Welcome to G Fun Facts Online. Every time you stream a movie, send an email, or ask an AI a question, you are using a data center. These colossal digital factories are the backbone of our modern world, but they have a dirty secret. They produce a tremendous amount of heat. Keeping these servers from melting down is one of the biggest challenges in technology today, and it's forcing engineers to look for solutions in the most extreme places you can imagine: the bottom of the ocean and the cold vacuum of space. The problem is a simple matter of physics. Every single computation converts electrical energy into heat. As we pack more and more processing power into smaller spaces to handle the explosion of data from AI and the Internet of Things, the heat density has skyrocketed. Traditionally, data centers use massive, energy-guzzling air conditioning systems, which can account for up to 40% of a data center's total energy bill. This not only costs a fortune, but also has a huge environmental footprint, using vast amounts of electricity and fresh water. So how do we solve this thermal crisis? The answer might lie in harnessing the natural cooling power of our planet and beyond. At its heart, a data center is just an energy conversion machine. It takes in electricity and turns almost all of it into waste heat. The goal of thermal management is to move that heat away from the sensitive electronics. We measure the efficiency of this process using a metric called power usage effectiveness, or PUE. An ideal PUE is 1.0, meaning every single watt of power goes into computing. Of course, that's just a theoretical dream. In reality, a really good land-based data center might achieve a PUE of around 1.1, but the global average is much higher, showing there's a lot of room for improvement. Over the years, we've gotten smarter. We learned that keeping data centers at freezing temperatures was incredibly inefficient. New guidelines allow them to run hotter, saving energy. We've developed clever techniques like using outside air in cool climates, or evaporating water to cool the air. And as processors get even hotter, we're seeing more liquid cooling, piping liquid directly to the chips, or even submerging entire servers in a non-conductive fluid. But these are all optimizations for land. The most radical solutions lie far beyond the server room. The first stop on our journey is deep underwater. The idea of putting data centers on the ocean floor sounds like science fiction, but it's a very real and very effective solution. The logic is simple. Use the consistently cold, deep ocean water as a giant, natural, and completely free heat sink. The primary benefit is the near elimination of energy costs for cooling. In these systems, seawater is piped through radiators attached to the server racks. The server heat is transferred to the cold water, which is then harmlessly discharged back into the ocean. This is way more efficient than air cooling, because water is a much better conductor of heat. The most famous test of this concept was Microsoft's Project Natick. In 2018, they deployed a 40-foot-long cylindrical vessel, basically a giant submarine data center, 117 feet deep off the coast of Scotland. It held 864 servers and ran for 2 years. The results were astounding. Project Natick achieved a power usage effectiveness of just 1.07, a number that makes land-based operators incredibly jealous. But the most shocking discovery was the reliability. The servers inside the underwater vessel had a failure rate that was only 1/8 of an identical set of servers running on land. That's an 800% improvement in reliability. Why? The researchers believe it's a combination of 3 things. First, the vessel was filled with pure dry nitrogen, not the corrosive, oxygen-rich air we have on land. Second, the deep ocean provides an incredibly stable temperature, eliminating the physical stress on components from heating up and cooling down. And third, there were no humans. No one to accidentally bump a server rack or jostle a cable. The entire operation was lights out. Project Natick also proved the sustainability of the concept. It was powered entirely by renewable energy from the local grid's wind and solar farms, and it used zero fresh water for cooling, a huge advantage over land-based systems. While Microsoft called Natick a research project, and hasn't announced commercial plans. It proved the concept worked, and others have taken the baton and run with it. Chinese companies are now taking the lead in commercializing underwater data centers. Off the coast of Hainan Island, the world's first commercial underwater data centers being deployed. The plan is to sink 100 data cabins, each a 300-ton pressurized vessel. The full facility is projected to save 122 million kilowatt-hours of electricity and 105,000 tons of fresh water every single year compared to a land-based version. Chinese companies claim this method can slash the energy needed for cooling by about 90%. There's another benefit too: speed of deployment. Instead of a multi-year construction project, these data center modules are built in a factory and then simply deployed at sea. This manufacturing approach means they can be brought online much faster to meet demand. Of course, operating high-tech gear on the ocean floor isn't easy. The vessels have to withstand immense pressure and the corrosive effects of salt water. Maintenance is a huge challenge. Because the model is lights out, the components have to be incredibly reliable. When something does break, repairs are complex and expensive, though some newer designs incorporate an elevator-like system to bring parts to the surface for easier access. There are also valid concerns about the environmental impact. Discharging waste heat could alter local water temperatures, and while initial studies suggest the effect is minimal, we need more research on the long-term ecological impact of large-scale deployments. As a less extreme alternative, some companies are developing floating data centers on barges. A company called Nautilus Data Technologies has a 7-megawatt data center on a barge in Stockton, California. It uses a closed-loop system to draw in river water, use it to cool the servers via a heat exchanger, and then returns the water slightly warmer but with no chemical contamination. It's a great middle ground, offering the efficiency of water cooling with much easier access for maintenance. So we've gone to the bottom of the ocean. Where else can we go? The next logical step is up. To the final frontier: space. The idea of putting data centers in orbit is gaining serious momentum, with visionaries like Jeff Bezos predicting they will exist within the next 2 decades. But space presents a thermodynamic paradox. It is both incredibly cold in the shade and intensely hot in direct sunlight. More importantly, it's a near-perfect vacuum. On Earth, we rely on convection, the movement of hot air or liquid, to cool things down. In space, that's impossible. The only way for a space-based data center to get rid of its heat is through thermal radiation. It has to literally radiate its waste heat away as infrared energy. This means a data center in orbit would need massive radiators, huge surfaces, designed to efficiently dump heat into the void. While the background temperature of space is near absolute zero, designing a radiator big enough to handle the heat from thousands of servers, while also dealing with intense heat from the sun, is a monumental engineering challenge. So why bother? One word: power. A space-based data center could be equipped with huge solar panel arrays, giving it access to a near-constant and abundant source of energy, completely free from Earth's power grids. This is the key to the vision of creating gigawatt-scale computing clusters in orbit. But even that isn't simple. A data center in low Earth orbit would spend part of its time in Earth's shadow, meaning it would need a massive battery system to keep running. And the thermal challenges are just the beginning. The biggest threat to electronics in space is radiation. Earth's atmosphere and magnetic field protect us from a constant barrage of cosmic rays and solar radiation. In orbit, servers would be directly exposed. This radiation can flip bits in memory, causing data corruption, or even cause permanent physical damage, frying the electronics entirely. To survive, the electronics must be radiation hardened. This is a complex and expensive process. It involves using heavy shielding, building in multiple layers of redundancy so if one part fails, another can take over, and using specialized manufacturing processes that are inherently more resistant to radiation. This all adds significant cost and complexity, and it often means that space-grade computer chips are several generations behind the cutting-edge processors we have on Earth in terms of raw power. And then there's the cost. Even with companies like SpaceX driving down launch prices, sending tons of server hardware into orbit is still astronomically expensive. Maintenance would be another nightmare. Like their underwater cousins, orbital data centers would have to be designed for perfect, lights-out reliability. Any repairs would likely need to be done by sophisticated robots, because sending humans would be far too expensive. Finally, there's latency. For applications that need instant responses, the time it takes for a signal to travel from the ground to a satellite and back could be a deal-breaker. However, for many of the most demanding computational tasks, like training massive AI models or processing huge batches of scientific data from Earth observation satellites, that delay might be perfectly acceptable. In fact, processing data that's already generated in space, right there in an orbital data center, could be far more efficient than beaming all that raw data back to Earth. So where does this leave us? The journey from simple water-cooled mainframes to the futuristic concepts of subaquatic and space-based servers shows just how far we're willing to go for more computing power. Underwater data centers are no longer just an experiment. They are a tangible, near-term solution that offers incredible energy efficiency and reliability. Space-based data centers are a longer-term, more audacious vision. The challenges are immense, but the allure of limitless solar power and the potential to move heavy, energy-intensive industry off our planet makes it a future worth pursuing. The future of data probably won't be in one single place. It will likely be a hybrid ecosystem: hyper-efficient data centers on land, rapidly deployable underwater pods serving our coastal cities, and specialized orbital platforms performing massive calculations high above our heads. The quest to cool our digital world is pushing the boundaries of engineering, forcing us to redefine our relationship with energy and information. And in doing so, it's shaping the very future of the digital age.